I'm continuing the PCB study. Is that I was at a conference listening to this woman that had done the research. PCBs can accumulate in the fatty tissues of your nervous system, including your brain. And she was curious as to whether people that were absorbing it from their food, from eating the fatty tissues in local fish, if you get a fishing license and you read the data, it says whenever you prepare the fish, you should scrape as much of the fat off as possible, because there's still PCB contamination all over the place in New York State. Anyway, so she ran a classic, she had rats in her study groups, and she ran a classic behavior experiment that is kind of an experiment on patience or lack of patience. And your two groups get tested the same way. They get this device, individual rats in little enclosures, and you do a bunch of rats in both groups, because you don't want to do just one rat and one rat, because if you get a bad rat in either side, it's going to mess up. You do like 100 rats and 100 rats. That's why they did thousands and thousands of vaccines, because you do just a few, you can't really trust the results. One outlier is really going to skew your results. So, one by one, they did the rats. Rat in an enclosure with a device. Here's how the device works. Rat goes up, presses a little bar, gets a piece of food. Goes up, now it needs to press the bar twice to get food. Then it needs to press the bar 4 times, and then 8 times, and then 16. You're starting to get the idea. Every time it wants food, it's got to press the bar twice as many times as it had pressed it before. And they put observers on, watching the rats, and you put the device in, you start your clock. And what's your end point, right? You're telling your people, when do you turn the thing off? When they move away from the food dispenser and are away from it for at least 5 minutes, at the end of the 5-minute period, because you've got another clock that you're timing how long they're away. When that clock hits 5 minutes, you stop your main clock. And that will tell us how persistent they are, how at some point they lost patience with the idea and they went away and they just didn't feel like coming back. The interesting thing about this was the woman out there goes, let me tell you the results, because I don't know how to interpret these results. The rats with the PCBs in their systems would not stop. They went for hours and hours and hours. They got the device up where they had to hit it thousands of times in order to get the next piece of food. And they actually started to do things that this is a standard test they've run on rats forever. They were doing things nobody had ever seen rats do for this. They'd get kind of like loosened up in their little enclosure, and they'd come up to the bar, and they'd get their feet out, and they'd go, and they'd keep doing it until a piece of food dropped out. The control groups had given up within an hour, a couple hours. The experimental groups were going for a day, just would not stop hitting the bars trying to get food. And the woman that ran the test went, what does that mean? I have no idea. I don't think we're testing patience here anymore. I don't know what this behavior means, and I certainly don't know what it means to people who are getting this stuff in their brains. And that's part of the fun of science, where sometimes you go, okay, this will happen or this will happen, and that happens, and you go, what the heck is this? And then you're trying to come up with a hypothesis to test your very, very weird results. So, a couple other terms to throw out that have to do with confounding factors. When you run tests on people, you've got your two groups. One group is actually being tested, the other one is being given a test, but whatever your variable is, they're either getting a different version of it or not getting it at all. Sometimes your variable literally varies. If you're running a test on vitamins, you really can't give your control group no vitamins whatsoever. So you're giving your test group a certain amount and your control group kind of a low base level amount, because Ethics is a confounding factor as well. But you don't want your two groups to know which group they're in. So a blind experiment doesn't let either of your groups, you don't know you're getting a placebo, you don't know you're getting a real thing. You know you could be, because we tell you that going in, but you don't know which you're getting. It's a blind test. They decided about 50 years ago that if I'm giving you the test, if I know which group you're in, I may not treat you the same way. If I know you're really getting the drug that we're testing, I may talk to you more about side effects and more about feeling better and be a little bit more concerned with keeping track of you, because we really need to track, side effects and stuff. Whereas if I know you're not getting the drug, I may be more inclined to talk about getting worse, because we're not expecting the drug to do whatever it's supposed to do, and maybe not talk as much about side effects, and maybe not track you as much for side effects as for illness. And they ran tests on this and found out doctors did tend to skew. They checked them for certain key phrases and concepts, and they found the doctors did treat people differently if they knew which group they were in. So most tests now are double blind, where the doctors have a bunch of bottles, like vaccine bottles, all numbered. Your test subject 106, here's test bottle 106. The company that packaged it knows whether you're getting the real thing or not, but I don't know which of the bottles has vaccine in it and which of them don't. Because they're set up so that they look the same. And so I can't treat you differently because I don't know which group you're in. That's a double blind. Triple blind, which they're just starting to do more as a general regular thing, is at some point, these tests get very, very complicated, and there are lots and lots of numbers to crunch. And typically you hire people to look for efficacy and test the numbers and do this and do that. And somebody at some point went, does it matter that they know which group they're crunching the numbers on? Because sometimes what your decision making isn't just straight math. Is it you're weighing factors and such? And are they weighing them differently if they know they're looking at the test group versus the placebo group? And folks went, well, heck, we don't know. Let's just not tell them. So triple blind, the number crunchers don't know which group is which. When you think about it, that makes a lot of sense. Okay, other things to do with scientific method. I read a blog written by a researcher. The researcher is a pharmaceutical researcher. And it's a very popular blog among people that are science people and are researchers themselves, but also science people like me. And so it's interesting to read the entries, but it's really interesting to read the comments. Because these people know how all of this stuff works. And when they say that a study is a bad study, they explain exactly why. And then you read it and decide whether their opinion is a good opinion or not, but you have to know enough about it to be able to judge that yourself. Because we are peers, we have similar training, we have similar backgrounds, we have similar understandings of what's going on. And that's how science is supposed to work, where you're at some point in your testing, somebody who understands it should be taking a look at it and giving you pointers or criticisms, or pushing you in some directions. In some cases it could be mentorship, in some cases it could be colleagues. In the type of research that I did, which is research at the university level, now I worked in a lab with a guy who ran the lab, but what I worked on, he didn't work on. So I didn't have anybody at the university who really worked in my area who could kind of mentor me and help me along. I could ask him questions about certain things, but the meat of my research was kind of just me, and I didn't know anybody else doing it. That's not unusual at university research, just in case you're wondering, because you can't read the concepts. It says that's it? That's peer review? Peer review is when people who understand get a chance to look and criticize your stuff. If you're working in pharmaceuticals, the guy in the next cubicle over is available to do stuff. So in industry, peer review is very much an ongoing process where you always have people in the know to kind of let you know, okay, no, we tested that and it didn't work, or, oh, that looks really interesting. What if you tried this to kind of you know. But very often in university research, the first time a peer looks at it is when you've done all your research, you've written it all up, and then you send it off to get published, and the editor looks at it and goes, okay, who do we have on our list that knows this stuff? And it goes out to what they call a reviewer, who looks it over and decides, a lot of times, yay or nay, you know, yeah, this is worth publishing, or no, it's not. Sometimes they send criticisms back and forth to the researchers, you know, can you do this? Can you tell me this? You know, you need to redo this. Like with mine, it's like, wow, this is part of the paper is way longer than it typically is. You may need to cut this out. And I went back with, well, that process, I don't know how you learned to do it, but I couldn't find any written source to tell me how to do this. I had to develop it myself, and I figured it was good to get it on paper for other people facing the same problem. And went back to the reviewer, and the reviewer probably, you know, went and looked and went, oh yeah, he's right. I don't really remember how I learned to do that, but it's not written anywhere, so yeah, it's a good thing to leave it in the paper, so it was left in the paper. But it's not unusual for you to do your research and send it off and it gets rejected. And then you either have to start from scratch or fiddle with it in a way, or send it off to a different journal. The journals have rankings. But that's peer review at the university level is a little bit different than peer review in the industry level. I gotta write peer review here down. This is not an artifact. This is another aspect of modern scientific method. Another thing about science is that it's done by people that are running out to get the ice cream truck. And as such, we have our own prejudices, we have our own, the background that we're building on. Remember, spontaneous generation made sense until somebody came along and showed that it didn't. But when people discovered microscopic animals, it came back out. It's like, where do these tiny microscopic things come from? Oh, they must just come from the little particles of dirt floating in the water. So our human tendency to explain things in kind of simple terms, to see things the way that we expect to see things. There's way more tests that will show you that men are better at various things than women are, than tests that show that women are better at various things than men are. And that's because most of the time running those tests are men and not women. It's very unusual to find men running a test where the men don't do better. And it's, you know, the same thing's true. It's the influence of your own internal psyche. And that's a process called postmodernism. Now, this is a weird term that has different people define it in very different ways. The same neighborhood, but you'll see it defined in different ways. It was originally an art concept where there was a shift away from depictions of the world, which was starting to kind of fall behind photography. And it became expressions of the artist, is that it became a much more personal, internal kind of pursuit. Is postmodernistic art is very conceptual. And ultimately it's supposed to tell you stuff about people or stuff about the person doing it. And you can apply that to, you know, politics, to archaeology, to all sorts of different things. Is the world is driven by people's prejudices, basically. And what you try to do as a scientist is recognize and work around them. Obviously, if you run an experiment, you want it to turn out the way that you expect it to turn out. You have to be very resistant to kind of nudging it in that direction, to, you know, picking the wrong sort of math to throw into it, so that the math, you don't want the statistics to dance the way that you want them to. One thing that some people that are not in science find frustrating is science will come out and say something, and then not too long after that, somebody will come out and go, nope, that was wrong. Or, you know, we think this is going on, and somebody goes, no, we don't think that's going on. And But that's the way the system is set up. The system is set up to be tweaked and to be changed and to be, in some cases, completely replaced by something else. Spontaneous generation was kind of a science explanation of the world. It turned out to be wrong, and it got replaced by, more biological reasons. In the first chapter, we talked about how people's ideas about how the world worked have changed over time. But change is a huge factor in this. People that criticize evolution very often will go, well, look, Darwin thought this and that was totally wrong. Well, duh, yeah, it was 150 years ago. Of course, a lot of the stuff that he thought about the way the world worked turned out not to be the way the world worked. Didn't mean that his basic ideas were wrong. Didn't mean that all of his ideas were wrong. It just meant that, yeah, there's some things that we had to come in afterward and go, no, it doesn't really work this way. And there were other people whose ideas were kind of tossed out, and then little by little, some of them have crept back in because they were smart people, and there were aspects of what they thought were going on that weren't entirely wrong. Good old Lamarck, we'll talk about Lamarck later. One other thing I want to throw up here that has to do with modern science, and since we're doing biology here, we think of science as happening in a lab. We're in a lab here. That's an owl hanging from the ceiling in case you can't tell. What the hell's that thing behind his head? But in biology, you can't always do a test in a lab. You can't observe natural behavior in an unnatural lab. You can't snatch things out of nature that are maybe endangered and mess with them in the lab. You got to go out where they are and observe and test. Testing gets tricky when you're out in the field doing your studies out there. So all of the rules about variables and control tests and stuff, you try to make things as organized and as unprejudicial as possible. But just the act of observing, are you absolutely sure they don't know they're being observed? If they know they're being observed, is it changing their behaviors? But a lot of biological stuff is done with field study. If you pick the topic about research, is that a lot of animal research is field study, and when you start to read how they've done this, you realize an awful lot of what they're coming up with as conclusions is based on very little actual observation. Like a lot of what we know about whales, now we can tag them, that helps. But used to be field study for whales is you were just watching them come up to the surface. Is that, and there's that very much limits what you can and can't guess about what's going on under the surface. So, and some animals are just very hard to track, very hard to keep track of. Maybe you pick a group of animals that's more stuck in one place, and then you compare them to animals that are roaming. Maybe they don't behave the same way. The original wolf studies, where the alpha male concept came from, the guy who did those studies had a huge enclosure of captive wolves that had been kind of thrown together, and it kind of developed their own little packs. And years later, he did a lot more field study. He went out into the wild and he observed wolves under natural circumstances, and he eventually went, those original studies were just artifacts. What we were seeing were artifacts of the fact that we had put a bunch of unrelated wolves into an enclosed environment, even though it was big, and the behaviors within the group, the alpha male behaviors and such, that's not what I'm seeing when I'm out watching wild wolves. There's much more likely to be, if you're gonna have an alpha, there's much more likely to be an alpha female in the pack than an alpha male. And even the alpha concept doesn't apply as well when you're looking at a pack that is mostly related wolves that are dealing with the wide world. Is that his original results were an artifact of how he had set the experiment up under more controlled conditions. Okay, that's it for chapter 3, section 1.